Good morning, and thank you for joining us today. My name is Serena Pace, a field application scientist in NGS and Array, and I'm happy to introduce our speaker for today. Dr. Steve Moore is an associate professor of molecular and medical genetics at Oregon Health and Science University, who also directs the clinical cytogenetics and clinical molecular diagnostics labs of the OHSU Knight Diagnostics Labs. He has been at OHSU since 2009 and has been responsible for bringing CMA, NGS, and methylation arrays, among others, to OHSU. Steve has a keen interest in developing new technologies and in leveraging existing technologies to address healthcare inequity. I will now turn it to Dr. Moore to begin his presentation. Thank you.
Thanks, Serena. I really appreciate the kind introduction. And by way of introducing myself, give you a little bit of history. My dad has 30-plus pairs of khaki pants in a closet upstairs, many of which still have tags on them. I think I got the thrifty gene from him. And so what I'm going to talk about today is how to get more from the data that you're already getting. And the other, I think the other piece, I'm not sure how to go forward here. Oh, the big, okay. Big one, yeah. So the other thing I'd like to just kind of touch on and hope you have in the back of your mind is that not everyone can do NGS. Not every lab is prepared to do NGS. Not every lab is prepared to do optical genome mapping right now. And so there are labs that are still bringing up SNP arrays. And so hopefully this will, for those groups around the world, frankly, hopefully this will provide some insight in terms of how we can play around with the SNPs a little bit, especially in the oncology arena, to kind of get more information and not have to do additional testing in a lot of cases. So I just put up some examples here of the utility of SNP arrays, and the previous speaker just spoke on that a little bit in terms of the myeloma, but 17p-LOH, et cetera. But we're going to talk a little bit today just about the mosaicism that we see, also a determination of zygosity, HRD scores. Not going to touch anything on constitutional, so for this audience, it's all going to be cancer related. But we use and rely on SNPs extensively. Sorry, we rely on SNPs extensively in our on our constitutional and prenatal arrays as well. So this is the platform that we're using, and you can visit OGT to kind of take a look at it. It's a 4x180, and there is targeted coverage across oncology-associated genes and SNPs across the genome. And so again, we're going to talk a little bit about these different examples of how we use the SNPs and how we're using the arrays beyond just the copy number detection. So mosaic gains and losses in our hands are often difficult to detect, especially on paraffin samples. So I've given a couple of examples here. The idea is if you set a standard cutoff, which we have at 0.8 for deletions, and you have only a fraction of the population, say 30% with a deletion, you're actually not going to be able to detect that deletion unless you're looking at individual cells, which we tend not to do. We tend to score by populations. With the SNPs, however, so as you can see on, do I have a pointer? Okay. Sorry for those on that side. Hopefully you can see this, but the log2 ratio here is 0, which means it's normal copy number. But of course, you can see that the SNPs have 4 tracks, meaning that you have that we've actually lost an allele. So we're missing the middle track here, the AB allele track here, and so this is a mosaic loss. But we're not detecting it just using the oligonucleotides, and so the SNPs are massively helpful when we have low-level mosaicism. And the detection limit for the SNPs is around 20% because they tend to bin at 0 to 0.2 and 0.4 to 0.6, 0.8 to 1. We also use SNPs, and we've kind of really been excited about this recently, at determining, or to use SNPs to determine ploidy. And so this was a newborn female with an abdominal mass, a neuroblastoma. And by FISH, we really couldn't get the ploidy on this because, again, it was a paraffin, and so we struggled a little bit with copy number, et cetera. And, but does it matter? So, again, we see gains and losses here. Does it matter if it's a 2N, 3N, 4N tumor? And Everyone in the audience knows the answer to that. Yes, of course it matters. So we already do a similar type calculation when we're looking at triploidy. I'll come back to the neuroblastoma in a second. I.e. we're looking at an input DNA versus number of cells. So there's a little bit of math here, and ignore it if you want, but the idea is the input is an amount of DNA. So if you have a triploid cell or tetraploid cell, you're going to use fewer cells to get the same input DNA. And so if we're looking at, again, just a section of this neuroblastoma, and we have our expectations down here in terms of what we expect for our allele tracks based on the ploidy of 2, 3, or 4N. The only one that matches this, if we look at so here's our normal copy number. This is one loss and this is one gain here. The only one that matches that is 3N. So we can tell just by looking at the SNPs without being confounded by, again, FISH on the FFPE, that this is a 3N tumor, which has a better prognosis than the 2N or the 4N. Could do the same thing in other tumors, and so this was a case that we worked on. I wanted to show chromosomes here because I haven't seen any chromosomes yet. I may have missed some sessions, but did want to show some chromosomes. And so this is a near triploid ALL case. And FISH corroborated the results, but the outside reviewers were interested to know whether or not this might be a masked haploid or a doubled haploid. Now, it unlikely given the fact that we're seeing trisomies, but nevertheless, when we ran array, we ended up with a very similar kind of story where, again, taking any segment where you're N, 3N, or 2N here, you can see that the only predicted pattern that matches is the 3N. So this was a triploid and not a masked doubled haploid. This is an example of how we're dealing with this fire hose in the face amount of data here. So you see all kinds of gains and losses. This is an ovarian cancer. And gains and losses across the genome. Again, just to orient you, the chromosomes are listed across the top here, and there's 1, 2, 3, and so underneath each of those boxes, really, and we're looking at a whole genome view. This is the copy number view here, so we have gains and losses. Anything above the 0 is a gain, anything below really is a loss here. And then these red regions here are the regions of loss of heterozygosity. So in normal cells, we would expect there to be 3 tracks. AA, AB, and BB. And here you can see there's not only loss of heterozygosity associated with deletions, but also copy neutral loss of heterozygosity. So what do we do with this? Well, we can go through and analyze each gain and loss for gene content, which is hugely laborious. We can also look at a concordant NGS panel that we run and kind of march through each gene, and we do that as well. But is there another way to kind of describe this in lieu of these other two approaches, two types of approaches? And so it's an example of how we kind of get the first. And so with the array, obviously, we can pick up very small deletions here because of the focused nature of the array. So we still do that piece. And yes, we do march through and look at the individual genes. And this is another example showing a BRCA deletion here, and in a predicted frame shift BRCA deletion in a BRCA-like tumor. And I've seen a couple of talks about this. The HRD score is something that we use to kind of collate all this data and to give us a better sort of overall view without having to go in and look at all of the individual genes across all these segments. And so what is this HRD score? And again, you've probably seen this already. I think a lot of folks are using it now to describe this complex data. And so we look at the number of telomeric allelic imbalances. So that is the deletions or duplications basically at the end of the chromosome, but don't include a whole arm. Large-scale transitions, and this is just where the inflection points, as it were, and I'll show you that in a second. And then the HRD LOH score, and so this is just the loss of heterozygosity, and this tends to be the best marker, and I'll come back to that in a second. So in this case, for the HRD score, So the telomeric imbalances here, we have 0. You can see a normal copy number at the ends of the chromosomes here and here. The large state transitions are 2, so you have 1 here and 1 here. And then the LOH score is also 2. You have 1 here and 1 here. This is too small to count as a separate. Any guesses here? Anyone want to raise their hand and kind of go through this and tell me how many telomeric imbalances we have here? Exactly, there's 1. Yeah, thanks. And then large state transitions, anyone? 3, all right. And then LOH, Yasmin? 2, exactly. Okay, so that's how it works. It becomes relatively simple, and you can just march through chromosome by chromosome, generating a score, and then you create a sum at the end, and that sum is then compared against cutoffs that are in the literature and have been established for different types of cancer. So, for instance, sarcoma, the one on the left here in the top is breast cancer, and then on the bottom right here is the sarcoma. So for the HRD score, you know, the question here, and my apologies, this popped up too early, but do we need all 3? And so do we have to go through and count all these, or can we just really look at 1? So the copy-neutral loss of heterozygosity really represents more of what's considered the genomic scar, and so that's what we tend to be more interested in. It's something that's permanent. You've lost one of the parental alleles, and you can't gain that back, whereas a duplication, you can simply lose that. So we tend to focus more on the LOH component, and I'll show you an example of why that is. So if we have our pre-treatment sample here, and we have an HRD sum of 25, which is kind of lower moderate. Let's just say it's a breast cancer, which the cutoff is 42. But post-treatment, you can see that it's increased quite dramatically, but it's the telomeric imbalances and these large state transitions that have increased. And so these types of events are more likely to have occurred via treatment. We're not seeing an increase in the LOH, which is, again, more of a historical scar of the brachiness of these tumors. And so it's important for us, again, to put more weight on the LOH score versus the others. And the only way to get the LOH is from the SNPs. So we're not picking up the LOH unless we're looking at the SNPs. And so we can get a lot of this information from NGS, but really with NGS, what we need to be doing is looking not just at genotyping SNPs, which is what we're doing when we're sequencing very often, but we want to look at, in effect, non-genotyping SNPs. We want to look at very frequent SNPs, because those are the SNPs that are actually going to tell us something about the loss of heterozygosity. And unfortunately, unless you're doing whole genome sequencing, you're generally not sequencing the non-informative SNPs, which in our case are really the informative ones. And so this is just a recent report showing the difference between, and the correlation between NGS and SNPs when we're trying to address LOH. And as it turns out, you need about 40% tumor when you're doing NGS to detect regions of LOH around 10 megs, whereas we need 20% or so when we're looking at SNPs. So currently, the SNPs that we're using on the array are still better than what we're doing with NGS, although I know there's tons of folks in the audience that are going to disagree with that, but it's where I feel like we are right now. So one thing, and this is maybe just to try to bring us all together here, is that you need both. And so this is an example of a mosaic gain and loss. Most likely a ring chromosome. We weren't looking, or an ISO 9q. But what you see here is a gain of the whole of 9q and a loss of 9p mosaic. So the SNP patterns look identical, even though we have a gain and a loss, but the SNPs are identical. So So we're stronger together. Again, maybe this is a take-home for all of us in the room, in our country in general. We're stronger together, but we do need both, and it's important that we're looking at both things. And these things, the copy number and the SNPs together provide an awful lot of really important information. This is an example that we had just this week in a leiomyosarcoma, and what we saw was consistent with the leiomyosarcoma. We had a 13q deletion, a 10q deletion, but we had what looked like a homozygous deletion of RB, and I didn't show the gene here, but it's just directly under where this patch of oligos have dropped out right here. But the really interesting thing here is that there was about 20% normal cells that were infiltrating the tumor, such that you can see up here we still have heterozygosity in that region. So the normal cells that were there were heterozygous, and so we're not concerned now that maybe we need to talk with the family about increased risk because maybe they're carriers of an RB deletion, et cetera. And so we do have a homozygous deletion, but the normal cells are contributing a heterozygous genotype here. And so I think the take-home is that with the oligos, it requires a certain amount of oligos to give you a read because you're comparing against the control. SNPs don't care, right? So if you have the SNPs, they're going to hybridize. It doesn't really matter what your level is in your control. In that case, it's a completely independent experiment. So same thing with the P10 deletions. It's really important to understand if we had a homozygous deletion or if there was a heterozygous, maybe a constitutional deletion. So I'm just going to conclude so that we have some time for questions too. So as I just stated, the SNPs provide an independent confirmation of the gains and losses as a separate hybridization, but also it can give us this information because it doesn't require the same amount of DNA be present. As long as there's something to genotype, it will be. And the SNPs obviously have been massively helpful in our lab in detecting mosaic gains and losses. We've used them very frequently so that we don't have to go back and fish a tumor. Instead, if we look at the SNPs are going to allow us to determine the zygosity of that tumor. In fact, probably better than a set of fish probes would, especially on paraffins. The SNPs can be used to determine this brachiness, and this is the HRD scores that we talked about a little bit, and so we're using this currently for applications including ovarian cancer, breast cancer, and others, and we're starting to use it on sarcomas as well. And then the oligos and the SNPs together can provide a really powerful approach to oncology classification, and so that's, again, being able to use both and not just dismissing the SNPs or just sort of assuming the SNPs are an add-on, that the SNPs are actually a massively valuable part of the assay that you're running. And can provide a lot of additional information that you're not getting from just the oligonucleotides. And again, that some of that can guide risk stratification, classification, and treatment options, especially when we're looking at some of the BRCA genes and members of that pathway. So again, so that we have a bit of time here at the end, I just wanted to thank OGT for their kind invitation to share this experience. Again, when they asked if we had anything cool to talk about with regard to SNPs, like, yeah, I think we've got some cool cases, but also for me, it played into my thriftiness and can we get more from less? And I think that there's opportunities when we're looking at the SNPs to maybe get more than at least I thought possible. And I want to thank the lab, for having done the work. I didn't do anything that you saw here. The group here at CGC for the opportunity to speak in this great forum of sharing and of information and fellowship. It's so nice to be in person again. So thanks for the opportunity, and thanks CGC for putting the meeting together here so we could have this opportunity. And then thank you for your attention, and any comments or questions are welcome.
We have time for one or two questions for our platinum vendor.
It may be an obvious question, but one thought that I had is there any opportunity to understand or appreciate the presence of chromothripsis based on the SNP profiles that you're presenting?
Yes, but with the chromothripsis, we usually see that in these breast and ovarian cancers, and so we don't include that in the HRD score. So it's something that we haven't seen a lot outside of that context. So I'll admit I haven't spent a lot of time looking at it and trying to appreciate the SNP traces on those. So
yeah, but just from a pure discovery standpoint, you haven't sort of. I mean, I'm just wondering if there's a way to sort of evaluate the SNPs in a region. But I guess what you're saying is you would have to sort of pre-anticipate where to look?
It's just that when we do see it, again, it's in these cases where we're just really kind of focused on generating an HRD score, and part of that is you leave chromothripsis out, and so we kind of categorically just ignore those. So I haven't spent as much time looking at that. I'll go back and take a look at some of those, though. Like I said, we tend to ignore them just because of that, yeah.
Just might be a missed opportunity, because you'd think if you knew places to look for it, that you might be able to train a machine learning algorithm to then recognize it, generally speaking.
I said, no, that's a great idea.
Thanks.
I'll go back and take a look. Thanks for the insight.
All right, let's thank Dr. Moore for his presentation.